Newton's law of gravitation. Newton's law of gravitation is actually pretty simple. It's a force that exists between any two objects that have mass. The equation that predicts the magnitude of this force is the force is equal to big G, which is a constant, which I'll talk about in a minute, m1, m2, this is the mass of the two objects, divided by r squared, where r is the distance between the centers of the two objects. Now this g, the gravitational constant, not to be confused with the acceleration due to gravity, is 6.67 times 10 to the negative 11. Units are Newton meters squared per kilogram squared. Now when Newton first developed this, he didn't know the magnitude of this g. It's a very small quantity, and an experiment was done by Cavendish over 100 years later that determined remarkably well this value with very good accuracy. Okay, so here's an example, a very simple example. Calculate the gravitational attraction of two 1,000 kilogram masses 1 meter apart. So we just applied this equation up here, and there's the g value. The mass of the one, the mass of the other, they're both 1,000 kilograms divided by 1 meter squared. And here's the answer. Now, just to give you some insight here, this is just about a millionth of a Newton. A millionth of a Newton would be 10 times 10 to the negative 5. So we've got two fairly large masses here, that is 1 meter apart, but yet their gravitational attraction between them is very, very weak. So gravitation is an extremely weak force. It really only becomes noticeable when one of the masses is extremely large, like a planet. Okay, now we can use this formula to find the acceleration due to gravity. So what I'm going to do is, since weight, mg, is a gravitational force between a mass and the Earth, I'm going to set mg equal to big G times the mass of the Earth times m divided by r squared. Now, as you can see here, the m's are going to cancel. So therefore, g is equal to big G times the mass of the Earth divided by r squared. Now this formula can be used to compute the acceleration due to gravity. Now, it shows a couple of things. First of all, g is independent of the mass of the object. We saw right here that the mass canceled. So this is what we saw way back in the chapter on kinematics, when we were talking about free-falling motion. We said that the acceleration due to gravity was independent of the mass of the object, and this shows why that is. Also, this equation right here can be used to compute g on any planet, just as long as we know the mass of the planet. This is the mass of the Earth, but it would be the mass of whatever planet, and the radius of the planet. Okay, now here's a problem. We want to find the acceleration due to gravity, due to the Earth's gravity, at a distance of the moon. So in other words, we want to find out what g is when we're at a distance from the center of the Earth equal to the distance from the Earth to the moon. So there's big G. This is the mass of the Earth, and we're dividing it by that distance. This is the distance from the center of the Earth to the moon, 3.84 times 10 to the 8th meters. Now this comes out to be 2.70 times 10 to the negative 3 meters per second squared. Now, if you go back, and I'll leave this as an exercise for you to do, and compute the centripetal acceleration of the moon, you'll come out with a number that's extremely close to this value. And what that does is it illustrates the fact that the centripetal acceleration to the moon is due to the gravitational acceleration that the Earth is pulling on the moon. Just one last thing about this equation up here. Notice that if you know g and you know the radius of the Earth, you can calculate the mass of the Earth. And this is really how the mass of the Earth was first determined. G, of course, was known for a long time, as was the radius of the Earth, known for a long time. But the mass of the Earth was not. So when Cavendish finally got an experimental value for this that was accurate, the mass of the Earth was calculated pretty quickly. Okay, so now we're going to talk about planetary motion, and we're going to discuss Kepler's laws. Kepler's first law says the orbit of each planet around the sun is an ellipse with the sun at one of the focus. Okay, so if you look at this diagram around here, you can see there's a planet orbiting around the sun. This shape here is an ellipse, and the sun would be at one of the focus points of the ellipse. Okay, Kepler's second law says that each planet moves so that an imaginary line drawn from the sun to the planet sweeps out equal areas and equal times. Okay, so, again, looking at this diagram here, if the planet is moving around in this path right over here, for example, compared to this path over here, here, because the planet is closer to the sun, it's moving faster. Here it's moving slower, but these two intervals here would be equal in time. And if you computed this area here and this area here, these blue areas, they are equal to each other. That's what Kepler's law, second law, says. Kepler's third law says that the ratio of the square of the periods of any two planets around the sun is equal to the ratio of the cubes of their distances from the sun. Now, we're going to actually derive this from Newton's law of gravitation and what we know about centripetal force. So to begin with, we're going to set mv squared over r, which is the equation for the centripetal force, equal to the gravitational equation. And the reason why we're going to do that is because a planet that orbits in a circular path around the sun, it needs to have a centripetal force in order to keep it in a circular path. Where does that force come from? It comes from this gravitational force between the planet and the sun. Okay, so we're setting those two equal to each other. We can see that the masses of the planet canceled, and we're left with v squared equals to big G times m. This would be the mass of the sun, in this case, divided by r. Okay, now, first of all, we mentioned this term period. Now, period is the time for one complete orbit. So the period would be the time for one complete orbit around the sun. So for the Earth, for example, it's 1 year. So we can say, therefore, that the velocity of a planet is equal to that distance, which is the circumference of the path, circumference of the circular path, 2 pi r, divided by the time it takes to go around once, the period t. So what we're going to do is now substitute that in here. So we've got to square each one of those terms. So we get 4 pi squared r squared divided by t squared is equal to big G, mass of the sun, divided by r. Now we're going to solve for t squared. We're going to do that by flipping both of these equations, taking the reciprocal, doing some cancellation, and we end up with t squared is equal to 4 pi squared r cubed divided by gm. Now, we want to take the ratio of the squares of the periods of any two planets. So this might be planet 1, and another planet 2 would have a similar term. So if we divide the t1 by the t2 squared for the two different planets, and then on the other side of the equation, divide this term for planet 1 divided by a similar term for planet 2, the four constants would cancel, which is the 4 pi squareds and the gm, which would leave us with this formula, which says exactly a mathematical statement of Kepler's third law. By the way, this is valid when comparing satellites of the same parent body. So in other words, this has to be two planets that are, for example, orbiting the sun. And the reason why that's true is because the two planets must have the same value here, this capital M, which we canceled out when we did the ratio.